Hello, my name is Chris Rios, and today I'll be discussing the use of IT, comparative effectiveness, and I'll be discussing the two assignments assigned today. So we will go ahead and start with the mini comparative effectiveness study. So in the assignment, it's set to identify at least two patients from the data table, which is shown to the right. We're supposed to select the possible controls at random utilizing the lowest random numbers. As you can see, that column is the last column in the table. And we're also supposed to match with the corresponding age, and we're also supposed to show the Kaplan-Meier survival plot. So we'll be going through the steps of doing that today. So as you can see here, we have our data table and we have a closer view at it. In this case, we'll be looking at two specific patients. In this case, will be patient 1 and patient 3. They're both highlighted in green. And we are going to go ahead and match them with their appropriate age. As you can see from the table here, there are at least two types of cases where the patients receive intervention, and there's 7 cases where the patients did not. And you can determine that by column 3, where it says receive intervention, yes or no. So in this case, case 1 will be the one that is highlighted in blue, and the ones that are highlighted in red will represent case 2. And I will go in a little bit more into detail how those cases were determined. We're also going to calculate as our very first step the standard deviation, which will be done through Excel, and that can be done using the standard deviation function, which is standdef, and you can just highlight the column of age and you can get the standard deviation. In this case, the standard deviation came out to be 8.89, and we'll see how we can use this to our advantage to calculate the ranges, which will determine what cases belong to which case. So in our last slide, and continue from where we left off, we calculate the standard deviation, which can be done all in Excel. And now we want to use the standard deviation to go ahead and calculate the ranges, which will help us classify what patients fall into what case. So since we're specifically looking at patient 1 and patient 3, we're going to use their standard base age and add and subtract the standard deviation that was calculated. So for case 1, the base age is 865, and we're going to add and subtract the standard deviation, 8.89, and see what patients fall within that range. So in this case, when you add and subtract 8.89 to 65, you get a range of 56.11 to all the way to 73.89. In this case, patients 2, 8, and 9 all fall under this range, and they can be considered under case 1. So similarly for case 2, we'll use the base age of 84, which is from patient 3, and we'll add 8.89 and subtract 8.9 to find the ranges, and we'll get a range of 75.11 up to 92.89. In this case, all the patients that fall under this case are 4, 5, and 6, and 7. And the reason we're doing this is to make sure that we're getting one sig away, or one standard deviation away, and seeing what patients fall under what. And we'll be identifying some controls as well. So in case 1, the controls will be patient 8 and 9, and the reason for this is because they have the lowest random numbers. Similarly for case 2, the patients 4 and 6 will be assigned the controls. They also have the lowest random numbers. So using the data that was last collected, or based on the ranges that we got and everything, we can come up with some additional tables that will help us do the Kaplan-Meier plot. So technically, what is the Kaplan-Meier plot? It's basically just an estimate that is used to measure a fraction of patients living for a specific amount of time after their designated treatment. So as you can see below, I have two different tables, one for the cases and one for the controls. where I'm looking at where a specific month period, which is for 4 months. I have the number of risks, the number with first fall and the number with first fall, the numbers without fall, the probability of no fall and not falling so far, and the percent of never falling. And so as you can see from the cases table, it helps demonstrate that two patients are specifically at risk, patient 1 and 3, and this can be calculated by subtracting the number of patients that are falling from the number of patients that are censored. To calculate the number of patients that are not falling, it can be calculated by subtracting the patients at risk from the number with the first fall. The same calculation can be done for the control using this very same concept. And to calculate the specific percentage of never falling in the control version, you have to use the percentage from the previous trial, or the cases in this case, to currently calculate the probability of falls. In this case, if we take month 2, we'll take the percentage of never falling, which is 100%, and we'll multiply it with the probability of no fall and not falling so far, which is 0.5 for month 2 in control, and we get when we multiply them, we get 50%. Now, using the data or the tables that we were able to create in the previous slide, we can go ahead and actually calculate or graph the Kaplan-Meier plot. So in order to do this, we looking at the previous two tables that we generated, we can take the months column and the percentage of not falling column and graph them. So in this case, as you can see, the independent variable is the number of the months. So in this case, we're looking at 4 segments, which is just 4 months, and the percentage of not falling is basically the dependent variable, and that's basically in the y-axis, and it can be graphed that way simply through Excel. Continuing on to the second part of the assignment, we're going to be analyzing trees, specifically event trees. So this is specifically very useful in the cases where we won't need to identify all possible outcomes and probabilities. They're basically a very representative and visual representation of what's actually can occur, and it can help us make predictions. So if you look to the right, I have a very simple model that can help us kind of understand what we're actually talking about. So it can be seen on this figure that the nodes, which are basically the circles, represent the pivotal events, and the lines coming from the nodes represent the possibilities. So you can also see that the probabilities are listed in the yellow numbers or yellow blocks, and they help us understand the probability of each case occurring. So in order to go ahead and actually fully calculate these calculations, we're going to take the previous example that was shown in the figure, and we're going to look at them at each branch level and try to calculate very significant calculations that we need to calculate in order to go ahead and calculate the final calculation. So if we're looking at the left image, we can see that this is the image or the event tree that was given to us, and we only have specific probabilities, and we need to calculate the other probabilities. So in order to calculate the other probabilities, if we take the branch or the line that says CHF, there's a probability of 0.15. To calculate the opposing branch of basically the opposite one, we would basically just do 1 minus 0.15 to calculate that probability, which would be 0.85. And the same can be done for all opposing branches, and you can see that they're calculated all in the next figure to the right. Now, using these previous probabilities that we calculate per branch, we want to calculate now the total probability per branch segment. So what we'll do is we'll take the base branch or the main branch, and we'll start multiplying it through each segment to go ahead and get the total probability. So if we're looking at previous MI branch, and we're going down all the way to CHF, we'll multiply those two probabilities. So we'll do 0.25 times 0.15, and we'll get that probability for that branch, that total probability. Now, if we're looking at the probability of BP less than 90, we'll take the main branch, which is previous MI, times the 0.085 of that opposing branch of the CHF, and multiply it times the probability of the BP less than 90 branch, which is 0.0870, to get that total probability. And the same can be done to all of them, and you'll see in the following slide how this can be useful for us. So picking up from the last slide, we can see that we calculate all the total probabilities for each segment of branches, and now we want to create a table that will help us analyze the total probability of the expected length of stay. So in order to do that, you can see that I kind of branched out the total branches and calculated total probabilities. So in the first column, it gives basically the branches segments of what we're actually looking at, of what endpoints we're looking at. So it's the same thing. So we'll multiply these probabilities to get a total probabilities, which is the probability of each branch, and then we'll multiply this with the length of stay to get that total probability. And using this total probability, we'll sum up and we'll get the expected length of stay. So in this case, when we multiply the length of stay times the probability of branch, and we're getting that total probability, we're then going to add the total probability of the total branch to calculate the expected length of stay. And that can be done for any event tree, and it will help us do some predictions and understand what can be interpreted from there. So I hope this is very helpful for you, and if you have any other questions, please feel free to reach out, and we'll be more than happy to help you. Thank you, and I hope you have a good day. Goodbye.